All right, welcome to video 2.2, all about Newton's laws. We did a little bit of this in class, but it always behooves us to go over it again in more detail. So we will start with Newton's first law. There are three of them. This one's familiar to some of you. As an object at rest will remain at rest, an object in motion tends to stay in motion unless it's acted on by an outside force. We're going to go about it maybe a little bit backwards. Let's say we have an object on which the net force is zero. Maybe that's just, a rock sitting there. There's no forces on it at all. Well, I guess if it's sitting there, there's gravity, but maybe there's no forces on it at all. Maybe I've got an object with a bunch of forces, but all of the forces are balanced, so the net force, the total force, is zero. In this case, we say the object is in equilibrium, and there's two ways to be in equilibrium. You can be in static equilibrium, where the object is at rest with a velocity of zero, and this is the one everybody thinks of as being equilibrium. You could also be in dynamic equilibrium, where the object is moving with constant velocity, and this is the one that always trips people up. If I'm skateboarding and my velocity vector is never changing, well, I can't be accelerating, I can't be speeding up, I can't be slowing down, and I'm not even changing direction. All of those things require forces, is what Newton's first law is saying is that if you want to speed up, that requires a force. If you want to slow down, that requires a force. If you want to change direction, that's still changing your velocity vector, that requires a force. The only things that don't require a force are sitting there or sliding along with nice constant velocity. So this is one of those key phrases, constant velocity, that you should always be on the lookout for in problems. Anytime you see those words constant velocity, your brain should go, aha, F net equals zero. Well, what if F net's not zero? What if we do have a force? Well, Newton's second law takes care of that, and we'll often refer to this one as NSL or N2L, just in case you see those little shorthand somewhere. When you do have forces acting on an object, it results in an acceleration given us by the equation F net equals ma. I suppose you could rewrite that as the acceleration is the net force divided by the mass of the object. And I want to point out two things here. First of all, that if we want to find that acceleration, we need to find the net force. And for that, we're going to use our free body diagram. The other thing that I want to point out is that mass is just a scalar. It's not a vector. And as a result, force and acceleration have to be in the same direction. If my force is this way, my acceleration is going to be perfectly parallel to it. They're scalar multiples of each other. That's their only option. So whatever direction the net force is, that is the direction of the acceleration. Last but not least, we're going to have Newton's third law, which talks about interacting objects. Anytime I have two objects interacting with each other, they might apply a force to each other. And in that case, I will always get a pair of forces. So if I have box A and box B, box A applies a force of A on B to B, and vice versa, F, B on A. And we call these two vectors an action-reaction pair. And I just want to note real quick that this action-reaction pair, each vector shows up on two different free body diagrams. So B's free body diagram would have that FA on B. A's free body diagram would have that FB on A. You'll never find them in the same free body diagram. And Newton's third law tells us that actually every force is part of these pairs, and that if you get these action-reaction pairs, they are precisely equal in magnitude, but opposite in direction. So, if we are ice skating and I push off on you, you go one way, I go the other. It's worth noting that the forces have to be equal, not the accelerations, right? If the masses of the two objects are different, they will have different accelerations. And maybe the best example of this, right, is, me jumping off the earth. If I jump off the earth, I push down on the earth, it pushes up on me. I go, a couple feet in the air. I get my jump. I'm still applying the exact same force down. If I apply a force of, say, 1,000 newtons, whatever, down, the Earth pushes me up with a force of 1,000 newtons. But I don't push the Earth as far because I weigh a little bit and the Earth has an enormous mass. So same forces, not necessarily same accelerations. And it's always worth identifying these on free body diagrams. It's nice to kind of look at those Newton's third law pairs when we can. So how do we do this? And again, we talked about this in class. We carefully draw our free body diagram using the AIDA method. We're going to set up a coordinate system, just like we did in kinematics. You always have to say what directions you care about. Oh, I care about, this is positive x and positive y. We'll actually see an example today also of something where x and y are not the directions we care about. And then we write down a Newton's second law equation for each direction and object. And we're going to get some more experience about how to do that. All right, so let's do a little example. Let's say Mr. Bates is pushing on two boxes, a red box and a blue box. What's going to happen? And we're going to ignore friction for now. So let's say I apply a 10 Newton force to these two boxes. And one of them is a 3 kilogram box and one is a 2 kilogram box. Well, let's go ahead and draw our free body diagrams here. For our red box here, I've got Earth providing gravity. I've got Mr. Bates providing a push. And I've got the blue box providing a normal force. The floor does not come in here. I guess you could actually say, yeah, the floor does provide a normal force as well. So if I look at my red box, right, I'm going to have, we'll call this, M red. We know it's 3 kilograms, but M red times G down and Fn up. I've got a 10 Newton F push this way. And I'm going to have this way, and I'll write this F blue on red. So there's my free body diagram for the red box. For the blue box, I've got, again, if I'm making my table carefully, I've got Earth providing gravity, the floor providing a normal force, and the red box also providing a normal force. Notice I, Mr. Bates, am not in the AIDA table for the blue box because, of course, I'm not touching the blue box. I'm only touching the red box. So for the blue box has M blue G down. We'll call this maybe FN2, I guess. It's always nice to give all your things distinct names. And to the right, I'm going to get F red on blue. And it's just worth stopping here and saying, hey, look, F red on blue, F blue on red are equal and opposite. These are part of a Newton's third law pair. They're in two different free body diagrams. All right, so what directions do we care about? Well, hopefully it's clear that we care about, we'll call this the positive x direction, parallel to the floor and perpendicular to the floor, the j hat direction. So let's go for my red box. I get in the I hat direction. Let's see. So if I focus on my x direction for my red box, I've decided right is the positive direction. So I have my 10 Newton push minus F blue on red equals M red A. In the j hat direction, actually I have something that's pretty boring. It's just F and 1 minus M red G equals 0. 0 in the y direction, which just tells me my normal force and my gravitational force happen to be equal in this case. So I want to find the acceleration of the system. I want to figure out what's happening, but you'll notice I'm missing something. I don't know F blue on red. So let's go ahead and look at my blue box, see if I can find any clues. My j hat direction here again is boring, Fn2 minus m blue g equals 0. That one's pretty boring. In the I hat direction, I just have F red on blue equals M blue times A. And you might think, oh, I'm stuck. I don't know what to do here. Well, there's two things I want to note here. One, we have a Newton's third law pair. F blue on red and F red on blue are the same magnitude. The other thing is, let's think about how the boxes move. If they're jammed together, right? If I move the red box 1 meter, the blue box moves 1 meter. If I'm sliding the red box at 1 meter per second, the blue box is moving at 1 meter per second. So their positions should be related. Their velocities should be the same. And so I actually can state pretty definitively that the acceleration of the red box and the acceleration of the blue box should be the same. We're going to get these kind of constrained systems all the time. And so I can put together my first two equations, right? And I'm going to write like this. I'm going to take my first equation and I'm going to write 10 newtons minus. Now, instead of writing F blue on red, I know that these are the same magnitude. So I'm going to write minus M blue A equals M red A. So I get 10 newtons equals M red plus M blue times A. So my acceleration is 10 newtons over their combined mass. And I just want to pause here for a second and say, we did a whole lot of work. We did a couple minutes of work writing free body diagrams and everything. And in the end, what we got is that pushing a 3 kilogram box and pushing a 2 kilogram box is kind of like pushing a 5 kilogram box. I do 10 over 5 to get an acceleration of 2 meters per second squared. But it's worth noting how this works out if I actually go and look at these internal forces, right? The system accelerates at 2 meters per second squared. So if I actually go find my forces, right, what's F red on blue going to be? F red on blue has to be 2 kilograms times 2 meters per second squared, or 4 newtons. So this gets pushed forward with a force of 4 newtons. Notice that means that F blue on red, this gets pushed back on with a force of 4 newtons. They're a Newton's third law pair. But it's getting pushed this way with a force of 10 newtons. So 10 minus 4 is 6 newtons. So the net force on the red box is 6 newtons, at least in the x direction. The net force on the blue box is 4 newtons. And you'll notice 6 divided by 3 is 2, 4 divided by 2 is 2. So that internal force works out to be 4 newtons and guarantees that the two boxes accelerate at the same rate. Let's talk a little bit about friction now. There's two types of friction, like I said, static friction and kinetic friction. So static friction is something that only acts when the object is at rest relative to the surface that it's on. And we write, what's interesting about static friction is that its value is changeable. If I have a box that's just sitting there doing nothing, like our turtle in the warm-up the other day, well, I'm not pushing on it, so the static friction force is 0. Oops, not 2, is 0. If I start pushing on it, right, if I apply a force of 2 newtons to it, static friction is going to push back with a force of 2 newtons. And if I crank myself up to 10 newtons, it'll try to push back with a force of 10 newtons. And it'll ramp up, it'll meet me newton for newton until I reach a maximum value. Static friction maxes out at some point. And once it maxes out, the object starts to move. And you've probably experienced this trying to move something heavy. You have to push harder and harder and harder until finally it gives way. And so when we're talking about static friction, all friction depends on the normal force. So what happens is that the maximum amount of static friction you get, the maximum amount of static friction you'll get is going to be equal to, so I guess it's correct to say that static friction is less than or equal to, and the max is just equal to. Static friction is less than or equal to some number mu times the normal force on the object. Mu is this number called the coefficient of friction. Now in this case, it's the coefficient of static friction. And this is a number. There's actually no unit to it. It's a number like 0.2, 0.5, 0.73. That kind of just tells you how strong friction is. The higher the number is, the more grippy the interface is. And the normal force also matters here in the sense that the more contact there is between the two surfaces, the harder the two surfaces are squeezed together, the more friction you get. So static friction goes up to this mu times the normal force. Kinetic friction, once you break through static friction and the thing starts moving, kinetic friction actually is just always precisely equal to mu times the normal force. So you can remember mu times the normal force for friction, just remembering that for static friction, that's a maximum value. For kinetic friction, that is the value. It's also the case for every surface that the kinetic coefficient of kinetic friction is strictly less than the coefficient of static friction. Getting the direction of friction right can be a little tricky. It is always opposite to the motion of an object across a surface. So figuring out that direction is often straightforward, but sometimes quite tricky. So we will need to stop and think about what direction, what friction is actually trying to stop. So you can kind of, again, see here that as you apply more and more force, static friction rises. And at some point you break through static friction and ka-chunk, you get into the regime of kinetic friction. So let's do a little bit of another worked example here. We've got the same two boxes, but I've stacked them. And now there is some friction with the floor, a mu-s of 0.2. And I want to know, how hard can I push before the boxes move? Well, again, let's start by drawing our free body diagrams. Now I'm going to sort of elide the AIDA table here, but let's look at our 3 kilogram box. It's going to have gravity down, mred g. It's going to have the normal force from the floor up. It's going to have my push this way. And if I'm pushing to the right, static friction is going to go to the left. There's actually one other force, though, which is the normal force from the blue box, which I'll call F blue on red again. And I want to note that if the thing's not to collapse through the floor, my normal force is actually going to get larger. My normal force is going to grow. In this case. I'm only going to stick to the red box for now, because it turns out that's the one that we're interested in. So if I write my equations for the red box, in the I-hat direction, so let me get rid of this other table for the moment. In my I-hat direction, I've got F push minus Fs. Now, you might ask, what is this going to be equal to? Well, again, I want to go all the way up to the maximum static friction force I can possibly get. Now, if I go even a smidge above the maximum static friction force, the thing's going to move. And so in physics, we often say, well, what is that limit? Where are they equal? And that's going to be the point that I need to exceed. So we're actually going to set this equal to 0. We're going to say, if I want to know how hard I can push and just equal the maximum static friction force. In my j-hat, and so if we look at our I-hat direction, right, that means I want to push equal to the maximum static friction force. And we were just told that the maximum static friction force is equal to mu-s times the normal force between the box and the ground. So let's go find that by looking in my j-hat direction. In this case, I've got Fn up, and I've actually got two forces down. I've got m red G, and this mysterious F blue on red. F, I promise I can write this clearly. F blue on red. And those are going to equal 0. So let's actually now turn our attention to the blue box. The blue box actually, as long as things aren't moving, only has 2 forces. It's got M blue G down and F red on blue up. So hopefully it's trivial to see that F red on blue needs to have a magnitude equal to MBG. So this is this force interchanged between the 2 boxes is just the weight of the blue box. So if I take this, I can actually say that Fn is going to be equal to M red plus M blue G. That is, if you kind of imagine the normal force is what a scale would read, if you put a 2 kilogram box on top of a 3 kilogram box, it looks like a 5 kilogram box. We'll just take gravity to be 10 here. So this normal force is 50 newtons from the ground. So in that case, I can just do 0.2 times 50 newtons, and I get that 10 newtons is my maximum pushing force. That means if I even push with 10.01 newtons, this stack of boxes is going to start to slide. It's going to start to move. All right. The last thing that I want to talk about today is what happens when your coordinate systems are not flat. So here we've got Spooky with mass m sitting motionless on an angled ramp. And I want to ask, what is the coefficient of static friction if Spooky's not moving? If Spooky is just sitting there, being Spooky, just sitting there. Well, let's draw a free body diagram. So here's, again, for Spooky. We've got the ramp. And the ramp's providing 2 things. It's providing a normal force, and I guess in this case a static friction force. And we have the Earth providing gravity. So in that case, we'll have gravity straight down. We'll have the normal force over at an angle this way, because of course it needs to be perpendicular to the ramp. And then for friction, we have to ask ourselves, well, which way is static friction? Is it? It's got to be parallel to the ramp. Is it up the ramp or down the ramp? And I always like to imagine with friction, what would happen if I turned friction off? Well, if I turned friction off, Spooky would slide down the ramp. So hopefully it's clear that our static friction force is up the ramp. So here is our drawing. And then the question is, what the heck? How do we work this out? Because I've got a vector that's straight down and then 2 vectors that are off at weird angles. If I try to do this in x and y, things are going to be a little wonky. So instead, when we have angles and stuff like this, what we're often going to do is we're going to adopt a totally different coordinate system. And the 2 directions our coordinate system are going to care about right now are a direction parallel to the ramp and a direction perpendicular to the ramp. So let's see what that looks like here. And you might notice for a moment that if I want in my I-hat direction, I have static friction pointing up the ramp. That's great. Minus, well, I don't actually have any other pure vector going down the ramp, but you might notice that gravity is neither, straight this way or straight that way. So kind of like we did with 2D kinematics, we actually have to break gravity into 2 components. We're going to have a perpendicular component and a parallel component. So let's do a little trigonometry. You might suspect that it involves the angle theta of the ramp, and you'd be right. I just want to point out that if this is theta, this angle is, 90 minus theta. So this angle is also the original theta. It's 90 minus theta. If we take this to be theta, notice that this component is on the adjacent side. So what we end up with is that the perpendicular component is mg cosine theta, and the parallel component is mg sine theta. And this is super important. You need to know this. You need to have this in your back pocket. We will do so many things on ramps this year, you will not believe it. Parallel component is mg sine theta. Perpendicular component is mg cosine theta. Know it. Love it. And the reason that this is really important is that changes all of these things as we go. So in my parallel direction, static friction is now opposing mg sine theta. And my normal force is opposing mg cosine theta. Now, in the j-hat direction, maybe it's clear that these add up to 0, because again, Spooky is not lifting off the ramp or burrowing down into the ramp. In my parallel direction, though, I also want these to equal 0, right? I also want Spooky is just sitting still. So if I take my j-hat 1, well, my Fn is going to be equal to mg cosine theta. Cool. And if I take my I-hat 1, I get that my static friction force is equal to mg sine theta. And I just want to note, remember, we know that static friction forces max out at mu s times the normal force. So what is the smallest possible coefficient of friction I can get away with here? What has to be the coefficient of friction? Well, if my coefficient of friction is as small as possible, that's going to be when my maximum force is exactly equal to mg sine theta. So I'm going to just take mu s Fn equals mg sine theta. We will often take, again, these edge cases, maximums or minimums, we'll often just set them equal to each other to find the kind of the limit, the boundary. Well, we know what Fn is. It's mg cosine theta. And now I can do a little bit of maths. You'll notice my mg's go away. I can divide away my cosine. And what I end up with is that the static friction that I need, the minimum static friction that I need, is actually equal to the tangent of the angle of the ramp. And let's just think about that for a second. What if my ramp is totally flat, if theta is 0? Well, in that case, tangent of 0 is just 0. Which means I don't need any friction at all to keep Spooky still on a flat surface. I put Spooky down, Spooky just stays there. As my ramp gets bigger and bigger and bigger, tangent gets bigger and bigger and bigger, and so I need a bigger and bigger coefficient of friction. What if I get to the absurdity and I now want to ask, what if theta is 90 degrees? And I'm asking what coefficient of friction will keep Spooky from sliding down here. And in that case, tangent of 90 degrees diverges, it's infinite. Which is to say, no amount of friction will keep Spooky from sliding down. And one way to think about this is my normal force goes to 0. There's nothing, unless there's something attaching Spooky to the wall, Spooky's not being pressed against the wall. Spooky will just fall. And that is our result. Now, we're going to talk a little bit in class next time about what happens if we want to push Spooky up the ramp and deal with kinetic friction and some other things. But for the moment, this is where we will leave it. I know that was a lot. So I just want to note again, what do we always do? We draw a careful free body diagram with the AIDA method. We apply Newton's second law. Oop, I missed a step. We pick the directions we care about. We set up a coordinate system. Sometimes that's X and Y. Sometimes, in the case of ramps, it is parallel to the ramp, perpendicular to the ramp. And then we set up Newton's second law in those directions and solve for whatever we need. We'll see a lot of examples of that over the next couple weeks.